Students, now let us continue with another problem on Cauchy's integral and Cauchy's generalized integral formula. Here is the problem. Evaluate integration over the curve C e to the power 2z divided by z plus 1 whole square into z minus 2 in the denominator dz, where C is the curve mod of z is equal to 3. So as usual, mod z is equal to 3 here. It represents a circle with the center as the origin and radius 3 units. Okay. And before going to the solution of this problem, you all need to resolve this into partial fractions. First, let us consider 1 divided by z plus 1 whole square into z minus 2. So you can resolve this as a divided by the first bracket of z plus 1 plus, since whole square is there, according to the rule of resolving into partial fractions, you all have to repeat it. Okay, so it will be b divided by z plus 1 whole square plus c divided by the last bracket. So this is what you get. Okay, now let us simplify this so as to get 3 separate resolved fractions. You have a into z plus 1 into z minus 2 plus b into z minus 2 plus c into z plus 1 whole square divided by the z plus 1 whole square and z minus 2. You see the denominator of both the terms, I mean from LHS and the RHS side gets cancelled, and you will have, yes, 1 is equals to a into z plus 1 z minus 2 plus b into z minus 2 plus c into z plus 1 whole square. Okay, now just put the values for z so as to get the coefficients a, b, c. Okay, so put z is equals to first as say 2. If you put z is equals to 2, this turns 0, this turns 0. You will have 2 plus 1, 3 whole square. It's 9c is equal to the left hand side, it is 1, it is constant. So c will get you 1 by 9. Okay, now put the value for z is equals to minus 1. You see that the first term gets cancelled, even the last term gets cancelled. If you put z as minus 1, you will have minus 1 minus 2, which is minus 3, b is equal to 1, and this gives you b is equals to minus 1 over 3. I hope it is clear. It's very simple. Now put z equals, okay, before putting any value for z, now we'll simply compare the coefficients of z square. Instead of putting any value for z, you can put z as 0 and get the value, but anyway we are not going to do that way. Okay, what we will do here is we'll compare the coefficients of z square. You see, you get z square when you multiply the two brackets over here. Z into z is z square into a. You get a z square, means a is the coefficient of z square from the first term, whereas second term does not contain any z square. The third term, if you expand this z plus 1 whole square, it is z square plus 2z plus 1. So there is a z square in the third term. So there is z square in the first and the last term with the coefficient as a in the first term with the coefficient of as c in the last term. So therefore right here comparing the coefficient of z square. So you get a plus c is equals to 0. You see that there is no z square on the left hand side. So directly you can equate it to 0, and a will be equal to minus c from this equation, but you have already found the value for c, which is 1 by 9. So minus c gives you minus 1 by 9, which is the value for a. Hence you have found all the values. Therefore e to the power 2z divided by z plus 1 whole square into z minus 2. You just have to multiply e to the power 2z to each of the resolved parts of this solution. Okay, so it is e to the power 2z. I'll keep it outside, but this part is been resolved as a divided by z plus 1. The value for a is minus 1 by 9 into 1 divided by z plus 1 plus the value for b value is minus 1 by 3, so minus 1 by 3 divided by z plus 1 whole square, and finally the value for c, which is 1 by 9, 1 divided by z minus 2. Complete the bracket. Now all you have to do is get this e to the power 2z inside the bracket. You have minus 1 by 9 e to the power 2z divided by z plus 1 minus 1 by 3 e to the power 2z divided by z plus 1 square plus 1 by 9 e to the power 2z divided by z minus 2. Okay, so this is what you get. Therefore, the integral over the curve C, I shall take it little down so that it should not mix up with the present bracket here. So integration over the curve C, e to the power 2z divided by z plus 1 whole square z minus 2 dz is actually equal to, let us separate each of the term because this complete term is equal to this, so we can separate our integrals and write. So it will be minus 1 by 9 integration over the curve C e to the power 2z divided by z plus 1 dz plus okay, there is a minus sign, so minus 1 by 3 integral over the curve C e to the power 2z divided by z plus 1 whole square dz plus 1 by 9 integral over the curve C e to the power 2z divided by z minus 2 dz. Okay, this is what you get. Now, yes, now we have to discuss whether each of these points belong to the given curve or they sit inside the curve. The curve C is given to be, yes, as usual, you are given with mod z is equal to 3. It is a circle with center 0 0 and radius 3. Okay, so let me check where it comes. Okay, so this is x-axis, y-axis, you have the circle mod z is equal to 3. Okay, now this point, if the radius is 3, you will have everywhere 3 over here. The point z is equal to minus 1. Z minus 1 means on negative x-axis. Negative x-axis means this, minus 1 comes here. So this belongs to the point, this belongs to the circle. So these two integrals we have to evaluate. What about z is equal to 3? It's 3, z is equal to 2. Okay, the point is here. So z is equal to 2 lies somewhere here. This is 2. Right, so if this is 1, okay, so both the points here, right here, a is equal to minus 1 and a is equal to 2 lie inside mod z is equal to 3. Okay, since all of both the points lie inside the curve C, so we have to evaluate these using Cauchy's integral formula, and in this case you have to apply Cauchy's generalized integral formula. Okay, so first we'll evaluate the first part. Therefore, integration. Before writing that, I have to write what is f of z. In each of the cases the numerator is same. Look at that, f of z is e to the power 2z. Okay, f of z is e to the power 2z. Therefore, integral over the curve C, f of z, okay, sorry, it is, I'll write the Cauchy's integral formula here so that it should not be a confusion. It will be like this. Wait a minute. Integration of the curve C, the z minus a dz. It is 2 pi I into f of a. To avoid just the confusion, we are going to use that. Okay. So here we are having e to the power 2z divided by z plus 1. Look at that. You have got that. Okay. So we have to evaluate this. So it will be equal to 2 pi I into f of minus 1. In the present case, the value for a is minus 1. I have shown you. Okay. So this is f of minus 1 will be 2 pi I e to the power minus 2. This is the value for the first part. We are done with it. Okay. Now the second part, I have to even write Cauchy's generalized integral formula here. I'll write it in a box so that it should not be a confusion for you. Integration over the curve C, f of z divided by z minus a to the power n plus 1 dz is equal to 2 pi I divided by n factorial nth derivative at the given point A. Okay. So here in second part, f of z is e to the power 2z only. The value for n is, since it is 2 here, n equals 1. Okay, and a is also equal to minus 1. So these are all the values. So since n is equal to 1, we have to work for the first derivative of f dash of z. So f of z, so it is f dash of z is 2 times e to the power 2z, because in formula we need to use it. So therefore integration over the curve C, e to the power 2z divided by z plus 1 whole square dz is equal to 2 pi I divided by n factorial. Here n equals 1, so 1 factorial f dash of a, f dash of minus 1 in this case. Okay, please write it properly. So this will be equal to 2 pi I divided by 1 factorial, which is 1. I'll not write it. So you have f dash of minus 1. So f dash of z is there. You just have to substitute in place of z minus 1. So it will be e to the power minus 2. 2 times e to the power minus 2, or it is 4 pi I e to the power minus 2. Okay, these are the values we have evaluated for the first two integrals. Now the final part, I shall be continuing it here. Okay.